In this video, we're going to talk about upper-level PV anomalies. Why PV anomalies? Well, previously we recalled that our PV equation, PV equals minus G times zeta theta plus F times d theta dP, was constant for any given air parcel provided that the flow is frictionless and adiabatic. So great, so we can come up with the absolute value of PV for a particular parcel or segment of air. But in order to really dig into this understanding of a cyclone, it might benefit us to think about where we have anomalously high or low values of PV given the current atmospheric structure. And so that's what motivates our study of PV anomalies. Let's go and consider first, where do we have a reservoir of high PV air? We typically have a reservoir of high PV air in the stratosphere, where we have high static stability, because those parcels of air will have greater than PV values that can be moved around and identified. And so we're going to begin our discussion of PV anomalies in the upper air near this reservoir of high PV air. But first, let's take a step back and ask ourselves, what is an anomaly? Mathematically speaking, we can separate any given value, A, into two pieces, an average component, A bar, and a perturbed quantity, A prime, or an anonymous quantity. If we rearrange this equation, we can solve for the anomalous quantity, A prime, as being whatever the total value is minus the average value under a particular segment. And so for our PV anomaly, what we're thinking here is, what is our anomalous value of PV given our PV distribution minus our average PV, say, at a given level of the atmosphere. So that then we can say that, it's anomalously high values of PV, say at 300 millibars, which may indicate the presence of a trough. And so let's go ahead and start drawing some of this out so we can start to see what this idea of a PV anomaly might look like. And so we're going to initially draw a box. And we're going to signify stratospheric air that looks like this. And we're going to indicate this air, giving us just some little hash marks here. And we're going to say that this air has PV that is greater than 1.6 PVU, which we know to be relatively high PV values, and is signified as stratospheric. Ultimately, if we want to consider a given level, we could say consider this red dashed line level. If we were to come up with the average value of PV at that level, we would then be able to indicate that we have a positive PV anomaly here, where we put our orange plus sign, such that this area has a higher PV value compared to the values that surround it at that level. How do we know that is the case? Well, we know that our air in the troposphere would have PV values less than 1.6 PVU. And so if we're less than 1.6 here, less than 1.6 here, but greater in the middle, we know that this then is an anomalously high value at this given PV level. So the question is, what gives us this positive PV anomaly? Thinking back to our PV equation, we have the static stability times the absolute vorticity. So is it a result of higher static stability that gives us a higher PV value, or is it a higher absolute vorticity value, or is it both? Because in order to have a positive PV anomaly, we would need values that are higher than average. And so what we're going to do is we're going to piece together to figure out which of these hypotheses is correct. And so let's begin and assume that we are going to construct an atmosphere that has a positive PV anomaly that is just the result of a vorticity anomaly. And so we will draw a new box for ourselves, similar to the one we drew before, again with this idea of a positive PV anomaly, indicating our stratospheric air with hash lines here. And so if we're going to have a positive PV anomaly plus PV at a given level due to a vorticity anomaly, then we're going to need to signify that vorticity anomaly. And so we're going to indicate it here in this cross-section, X with a circle around it as going into the page, and a dot with a circle around it as out of the page. The size of these two symbols will indicate the strength of the wind. And so where we have this strongest anomaly is where we would, by definition, have to have the strongest vorticity anomaly. And so here we are signifying our positive PV anomaly as a result of a positive vorticity anomaly. And so positive vorticity anomaly is going to have to be a cyclonic vorticity anomaly. And so that means we're going to have to go into the page on the eastern side and out of the page on the western side. And so we know that this might be maximized somewhere around 300 millibars. And because the atmosphere is in thermal wind balance, we know that the winds must increase and will increase up to this height, such that we're going to have weaker winds below, but still cyclonic, and weaker winds above, but again, still cyclonic. But since the atmosphere is in thermal wind balance, we can then start to say something about the temperature of structure of the atmosphere as well. And so we're just going to draw in some vertical lines here to indicate different portions of our cross-section. And so we know that where winds increase with height, where do we know cold air should always be? Correct. Cold air would always be on the left in the northern hemisphere. So we know that within our cyclonic rotation, this air will be cold. This also rings true because we know that then the level of our troposphere will be lower, as indicated by the lower edge here of our kind of 2 PVU surface. Call that the 2 PVU surface. Okay. Additionally, if that's cold there, then what must be around it? It must be warm air. So that's around our lower level circulation, where again we're used to interpreting thermal wind balance as winds increasing with height in the atmosphere. But going above our anomaly, we know that our winds decrease above this level. And again, as a result of our thermal wind balance, now winds are decreasing with height, and so we reverse where cold air would be. And so within our anomaly column here, we would have a warm anomaly, and surrounding it, we would have cold air. As a result of this structure, this temperature structure, we can now think about drawing in some isentropes. Recalling that for cold air domes, and warm air looks like buckets. And so if we think about our cold air being domed, we might get something that looks like this. Now, this is in our troposphere, and so maybe we have theta, theta minus delta theta, and theta plus delta theta, where theta is increasing with height as per usual. But within our anomaly zone here, now we have our warm, and so we're going to have warm pockets within our warm, and our cold domes and our warm pockets. And so what we get here is, in fact, both. We must have a positive PV anomaly with a strengthened static stability anomaly. And so when we started with just our initial positive vorticity anomaly, we coupled with that a positive static stability anomaly. And so our positive PV anomalies is the result of both a positive relative vorticity anomaly and a positive sigma anomaly. And so there is no ambiguity at all. Our positive PV anomalies are the result of both a vorticity and static stability anomaly. In a future video, we're going to talk about how then these anomalies can influence a depth of the atmosphere and are related to the life cycle of mid-latitude cyclones.